Hello and welcome back to Geology. Today I want to talk a little bit about landscapes and the hydrologic cycle. Now looking over here at the document camera, remember a landscape is the character and shape of the land surface in a region. And that shape of the land, or really its evolution, is what we call geomorphology. In fact, geomorphology is a study of the change of these landscapes. They involve landslides, debris flows, a variety of other features in the development of landscapes. So geomorphology and landscape are kind of interchangeable terms. So we can kind of link these two. Your book doesn't really mention geomorphology, but it's something I want you to know about. A universal agent on this planet that's instrumental in sculpting landscapes, geomorphology, is water. Water in both the solid and the liquid form, so in glacier or in streams, rivers flowing across their surface, plays a key role in the landscape evolution in geomorphology. Other terms we should know about: uplift. We've talked about uplift with mountain building. Subsidence occurs, is a downward movement, so areas may subside over time. And then another key term is this idea of mass wasting, which is essentially the downslope movement of material, tumbling or sliding of rock downhill. And usually here we have a gravitational energy that's pulling this material downslope. So these are our landslides, mud flows, rock falls, slumps, earth flows, debris flows, a variety of different downslope mass wasting materials. So all this belongs under this category here. Now, what are the agents of erosion? We mentioned these before when we talked about sedimentary rocks, but we're moving material, right? So moving water is one, streams, glaciers, air. And so all these can move material. And in fact, load is a term we use for material sediment that's being moved. So usually we describe it in terms of a river carrying a load, but a glacier can carry load. The wind, in fact, this air, or aeolian means wind, can move sediment around. And remember, erosion is simply the transportation of material. Now, deposition is where this energy drops off and the material loses its capacity to carry that load. And in that sense, we're going to see landforms. Some landforms are said to be erosional, which are carved and sculpted. Usually we see valleys, either gentle slope valleys or steep valleys. The other features we see are landforms that are depositional. So those are basins, deltas, alluvial fans. In the ocean, alluvial fans are really abyssal fans. They occur at the mouths of submarine canyons. Now, what energy drives the landscape evolution? So there's the internal heat engine, which is plate tectonics. They're making the origins, right? And the external heat engine, that's solar radiation. And really it's instrumental in driving weather and climate. And then the other one we talked about briefly was gravitational energy, which is pulling this material down slope. And your book mentions that it is a battle between the tectonic uplift forces, which are those due to the internal heat engine, versus the forces of gravitational and the external heat engines, which are causing erosion, weathering, right? And then the difference in elevation between 2 points is called relief. And so if we look at the relief of an area, we want to find the highest point on the map and the lowest point on the map and figure out the difference between those two. And then regions undergo subsidence or uplift, and the rates that your book says it's anywhere from about 0.01 millimeters per year to 10 millimeters per year. So they seem, remember 10 millimeters is 1 centimeter, so they seem relatively slow, but at a rate of just 0.15 millimeters per year, you can get uplift in 10 million years of almost 5,000 feet, 1.5 kilometers. So that gets significant over time. And usually the rates are a little bit faster. So this is actually toward the lower end. If I had even a 1 millimeter uplift rate over 10 million years, I'm going to get 10 kilometers of uplift, right? So a huge amount of uplift in that short period of time. Now, factors controlling geomorphology, the landscape. And there are several. The first one well, what is it? Is it glacial ice? Is it water? Or is it wind? What's the agent of erosion? So one thing we find with glaciers is they carve steep valleys. If you've ever been to Yosemite National Park, the U-shaped valley, very steep walls, flat bottom of the valley. So glacial carved, glacial steepening. Usually the ridges, if you've ever seen pictures of the Grand Tetons, these jagged ridges, those are glacially sculpted ridges, right? And also the sediment that's being transported, the load being transported to the glacier, well, it's moving big stuff and small stuff, and it's just dumping it at the end in these features called moraines. And that till in the moraines is poorly sorted, very different sizes. On the other hand, rivers carve these V-shaped valleys. A V-shaped valley, more rounded ridges, so not steep ridges. And if you go farther downstream, you'll see well-sorted sediment because some of the finer particles are carried farther than the larger particles. Near the headwaters of the stream, you'll see poorly sorted sediment. So the agent of erosion is pretty important there. The next one your book discusses is the steepness of the area, how steep the slopes are. Steeper slopes lead to faster velocities when material starts tumbling down. And that's really due to this gravitational energy. And then climate, if you have more rainfall, more precipitation, you're going to lead to more running water, more erosion, faster rates of erosion. Also, warmer climates can be more humid. They can cause increase in the rates of weathering. And remember, weathering produces weathered product, which is susceptible to erosion, which is the transportation. The next one is, well, what do you have? Do you have hard rock or soft rock? For example, in the East Bay of the San Francisco Bay Area, there are many ridges and gentle slopes, and much of the rock out there is shale. So it's a soft rock. But in the Sierra Nevada, where we have granites, we'll see steeper cliffs, which are rocks that are more resistant. So the stronger rocks will lead to steeper cliff, more resistant rocks. And then in terms of life activity, plant root action, vegetation, that helps stabilize slopes, whereas animal burrows and digging through the sediment will lead to slope instability. And the last, or the next topic here is older landscapes are more deeply eroded, right? So a young creek over time will develop a steeper profile. It'll cut into its bed. And when we start talking about streams and stream evolution, we'll talk about the process called down cutting. It's human activity. And even though we have a small contribution, it is significant. And our road building, mining, agriculture, ranching, deforestation has really altered the landscape, the geomorphology in many places. So one thing that happens, especially deforestation and paving, roads and concrete, will lead to more runoff. One of the things with pavement, that eliminates the ability of water to seep into and percolate and infiltrate into the ground. So it doesn't seep in, so instead it'll run off, right? So that makes a higher energy, more erosive power to carry load and material. Deforestation, well, this makes the slope unstable and leaves material available to transportation and erosion. Your book makes an interesting point. In the United States, if you were to gather all the areas that have been paved, roads, blocks, sidewalks, it covers more than the entire state of Ohio. So it's a huge area there. Now let's look at the hydrologic cycle. Now the hydrologic cycle is really, it describes water moving between different reservoirs or regions on Earth. So one of the largest regions on Earth are the oceans, and the oceans make about 96.5% of all the water on Earth. 96.5%. That means only 3.5% of the water on Earth is fresh water. And though that 3.5%, we're going to say that a little over 2%. So in fact, let's put 2.05% is glacial. And then the next important one is the groundwater. 0.94% is groundwater. and that's water that occurs in the subsurface. And just to compare, if we combine the freshwater lakes, and we would see that we only have 0.007%. These are lakes, freshwater lakes. And then for rivers, it's very small. Rivers are 0.0002%. These are going to be the streams. So this is for our freshwater sources. You can see that its glaciers are significant, but they're frozen. Usually glaciers are far away from regions where people live. But groundwater. So when we talk about groundwater, they'll be an important resource for us. Now, let's look at how this water is moving from one region to the next. And so solar radiation, or the external heat engine, is warming the sea, causing higher kinetic energy, and eventually we get evaporation. And one thing that I want you to understand is that for every gram of water, which is about 10 drops of water, that evaporation process extracts 540 calories per gram. So remember, a calorie is a unit for energy, a unit for heat or energy. So there's an extraction. We're taking that energy out. But then condensation. So the key thing about condensation, we're making clouds, and so basically it's water droplets. So we take the vapor, the vaporized material, and bring it back into the water state, right? So if you think about this, this is vapor here, and then this is back to a water or liquid, we'll put here, when you condensate. So those 540 calories that were available here now get released. And the key thing about this release of those 540 calories is that this is energy for storms, hurricanes, winds, right? So that's the energy that's going to drive our atmospheric circulation. Then we'll see, once there's enough water droplets up here in these clouds, you're going to see precipitation, right, which is rain, snow, or sleet, hail. And then some of that precipitation never makes it to the ground, and it'll go through plants and be breathed out of plants. So that's called transpiration. So I want you to know what this transpiration word is. It's plants using the water and then send it right back up into the atmosphere. You could see evaporation again over here as well. So sometimes we use a word, we use this long word called evapotranspiration to describe both the plant use of water plus evaporation together. A lot of the water will end up flowing down rivers back towards the ocean here, and so that's called runoff. So runoff is just a surface flow of material. Some of that water will infiltrate, percolate into the ground. So it'll infiltrate. I like the word percolation because percolation, just like a percolator, a coffee pot, will pick up material. And what happens is, as this water infiltrates, it's going to pick up minerals, calcium carbonate, silica, and that's later going to be the cement for making sedimentary rocks, right? And eventually that'll go into the groundwater, which is our underwater reservoirs there, aquifers. And we'll talk more about that as we go along. All right, so there's our hydrologic cycle. We'll stop here for now.